Now we will solve some problems to find the area of a region using double integrals. As I told you in the previous video, this is the formula of the area using double integrals. Let's look at the question. Find the area of the region bounded by the parabola y equals x squared and the line y equals x plus 2. Let me first sketch this region. Okay? This is the xy axis, and this is the famous parabola y equals x squared, y equals x squared, y equals x squared. Okay. What about the line y equals x plus 2? The line y equals x plus 2 is something like this. Okay. Let me extend the parabola. So we will find the area of this region by double integral. Okay. So we have the formula of double integral here. So I think the important part is to choose the a. We have two ways to choose the a. If you say the a is equal to dy dx, for instance, dy dx, and set up the double integral for this. Let's say the area is equal to, we don't have the function since we compute the area of the function, the area of the region. So for the a you write dy dx, dy dx. Let me write, what about the boundary of, what about the limits of integration? As you remember from the previous videos, what was the idea of double integral? How do we compute a double integral? If you first write y, for instance, if you first write dy, you draw a parallel line to the y-axis. You draw a parallel line to the y-axis, something like this. Okay, this is a parallel line. And you check where do you enter to the region. On this point you enter to the region, and on this point you exit to the region. So this point on the curve y equals x squared, so the lower limit is equal to y equals x squared. The upper limit is on the line y equals x plus 2, y equals x plus 2, and x is from this point, okay, we will find, to this point. If you make them equal to each other, if you say x squared, since y equals x squared and you have y equals x plus 2, if you make them each other, if you make them equal to each other, then you have this equality. If you solve this equality, you will see that x is either 1 minus 1 or 2. Okay, so x is from minus 1 to 2. And it's very simple to compute this double integral. Okay, it's the first way. It is the first way. If you choose dA as dx dy instead of dy dx, if you change the order of integration, then the area formula becomes double integral dx dy. Now let's check the region. Okay, let's check the region again. Since we first write dx here, we draw a parallel line to the x-axis. Let's draw a parallel line to the x-axis. This is the parallel line to the x-axis. If you draw from here, for instance, if you draw from here, the left curve is this. Be very careful. This is the left curve, okay, and the right curve is that part. Okay, this is the right curve. If you draw this parallel line here for instance, on the left you have a line y equals x plus 2. You have this line, okay, on the left you have this line, and on the right you have the same curve. So if you prefer to write dx dy instead of dy dx, you have two regions. You actually have two regions. Okay, let me clear also this one. So you have two regions to compute. Let's say this is region 1, this is region 1, this is region 2. Okay, so what do we have? So we have two regions, okay. Let's say this is R1 plus double integral on R2 dx dy. The rest is just to write the boundaries of integration, dx dy. If you look at the region R1, the left curve is what? The left curve is minus square root of y and the right curve is plus square root of y okay, from x equals minus square root of y to x equals plus square root of y, and y is in between 0 to 1. This is intersection point 1, okay. Plus on the region R2 you have y minus 2 on the left, y minus 2 on the left, and the same parabola, which is square root of y, on the right, and y is from 1 to the point 4. It is also the same. If you compute these two double integrals, you will exactly obtain the same numerical value.